So there's a lot of engineering that goes into determining exactly how deep the reinforcing needs to go on every application. And so there's a lot of quality assurance around this to ensure that this actually occurs. And to be honest, almost all, a great majority of corrosion issues with structures is around the fact that the cover hasn't actually been achieved or is spotty at best, okay? And this just sort of, this simple graph here just sort of describes how important this cover actually is, because obviously the chemicals are ingressing through the concrete through diffusion, and we know through Fick's second law that that's an inverse square rule. And so this graph is just a parabola on its side indicating the age of the structure versus the depth of penetration of, in this case, carbonation. And so we can see here that just by having a deficit of 2 millimetres of cover, we're decreasing the effective service life of this structure by 10 years. And the service life we're defining here is when the carbonation reaches the reinforcing, which is the most predictable part of corrosion. Once it actually reaches it and starts to crack, it becomes much more less predictable. And so that's generally the major part of the service life that we define when we're dealing with concrete structures. So how do we measure this? There are a range of tests that we can use. So the first one would be what's called a cover meter. Okay, quite obvious. Those of you who are familiar with eddy current will see this and go, oh, well, that's just an eddy current. That's exactly what it is. Effectively, we have some coils inside of a head. We pass some a current through that creates a magnetic field. We pass it over the concrete, and the reinforcing has eddy currents induced inside of it, and that creates a magnetic field back at our probe. And so that the strength of that field that we get in response from the reinforcing is proportional to the depth of the reinforcing. And so a cover meter is a ubiquitous device that's used in almost every single construction project out there to ensure that we achieve the cover that we want. And this graph here just talks about the type of accuracy that we can achieve. Cover meters have limitations, okay? So I've described that we have our reinforcing and we get a field strength from it. Unfortunately, there's more than one rebar inside of the concrete. In some cases, there's a lot of rebar inside of the concrete. And so the layout of the reinforcing controls quite a lot, the type of accuracy and whether we're actually able to achieve the accuracy that we need. And so this slide here just talks about different orientations and different spacings of reinforcing. So if we've got one bar, we get very good measurement of our cover. The red spots indicate times when our cover meter just won't work, okay? So I'm going to switch across now. You're going to find me moving through applications relatively quickly. So the next technology that I'm going to talk about is ground penetrating radar. And so ground penetrating radar is effectively using radio waves and transmitting them into our insulator concrete, and it effectively picks up changes in what's called dielectric. Let's simplify it and say conductivity, okay? So wherever we have a boundary where the conductivity changes or that dielectric contrast occurs, we get a reflection from that interface. And so ground penetrating radar is a very good technique for finding our reinforcing, okay? But we can also use it for finding other embedments inside of concrete. So it's used very extensively in the concrete cutting industry, plumbing, electrical industry, where they're looking for services inside of the slab because people like to bury plastic inside of the slab as well as the reinforcing. We also have something called post-tensioning, which are these high tension cables that we use to replace the reinforcing inside of concrete. You cut one of those, you're effectively reducing the tensile strength of your concrete substantially. And so ground penetrating radar, how it works is that we send our radio waves down into the concrete. They broadcast. They don't just go down in a straight line into the concrete, and we wheel it across using a wheel encoder. So we're measuring the distance of travel as we do this, and we're using that wheel encoder to fire the radar. As we wheel it across the surface, if we had a cylindrical reflector here, such as a reinforcing bar, we can see it before we cross over it. and the machine records the amount of time it took for that reflection to occur. As we wheel over the top of it, the time becomes its shortest, and then as we go past it, it gets longer. And so when we look at our B scan or our raw data with a ground penetrating radar, this cylindrical reflector turns into this hyperbolic shape that you can see there. And so these are the different types of imagery that we can get from a ground penetrating radar. So we have our basic B scan just here, where each of these hyperbola shapes at the top would indicate a reinforcing bar. Because we're using radio waves and it's just about a dielectric contrast, we can also see the bottom of the concrete, or if we have soil beneath it, we also get reflections from that. We have a process called migration, whereby we try to reconstruct the actual image of what is inside of the concrete using a mathematical formula. And so this is the same image but passed through this migration process. And you can see here now it looks a little bit more like what I'd expect to see if I sliced through the concrete. I would see the ends of each of these reinforcing bars. I can also arrange my scans that I do. I can do multiple scans parallel to each other, and then I can fit that all together like fit it all together and then slice it down in what we call C scans looking from the top. And so this is how we get this image here, where we can see a top view, and this is quite a good view for showing in an area and showing where the embedment is within that area. And then we can also go all the way to a full 3D image of what's going on inside of that. Ground penetrating radar costs a bit more than a cover meter, so generally it's not used for cover measurements, although it is better where we have tighter reinforcing. But where we tend to find that it's used a lot more is looking for multiple types of materials and looking deeper past the top reinforcing. So this image here just sort of talks about I get the reason why I put this slide in is because it's very interesting from a UT point of view, an ultrasonic point of view, just contrasting the fact that ground penetrating radar is almost the opposite of what we find with ultrasonics, whereby an air interface does not create 100% reflection, and so we can actually penetrate through that. You can actually do ground penetrating radar through a false wall into the concrete behind it, even with an air gap. Whereas with ultrasonics, if you didn't have access to the face of what you're actually testing, you wouldn't be able to test it. And so, but steel is the big reflector with ground penetrating radar. And so there is this opportunity to use ground penetrating radar and ultrasonics and create an image which fits together both of the main reflectors that we're interested inside of the concrete. Changing pace again, let's talk about strength, okay? The main non-destructive test for determining or estimating strength of concrete in the field is called a rebound hammer or a Schmidt hammer or a Swiss hammer. It has many different names. Effectively, it's kind of like a Lieb hardness tester, if you're familiar with those. And so what we're doing is we're bouncing a mass off of the surface, and the hardness or the rebound that we're getting, we correlate that using some laboratory calibrations to estimate what the compressive strength is. One of the reasons why I told you how changeable concrete is that we can't just have, it's not like stainless steel where we can just look at it and go, we've got this hardness, we've got this tensile strength. It doesn't work like that with concrete. We actually need to create a calibration for that specific concrete mix. And so if you don't have the opportunity to do that, which is quite common, where you're dealing with an existing structure and you have no samples of that you can actually test, there's various different ways that we can get around this issue. One of those being that we could set up a calibration curve where instead of using a line of best fit, we put a lot of the data above and only 10% below, so then the number that we get is inherently conservative. We could also do sort of a quasi-destructive, non-destructive combination whereby we take samples and use that to do a calibration as we go. Another technique that we can use for strength estimation is ultrasonic pulse velocity. So this is just time of flight ultrasonics, where we send a pulse, a compression wave, from one transducer to the other. And all we're really interested in is timing how long it takes for the pulse to go from one side to the other. That correlates very well with the amount of air that's inside of the concrete, which correlates very well with quality of concrete and also strength of concrete, okay? So we can use ultrasonic pulse velocity the same way that we do with rebound, but now we're getting information from the inside of the concrete as opposed to the surface of the concrete. One of the limitations is obviously we need to get access to both sides. So if I was to test on the floor just here, that'd be really difficult. I'd need cables long enough to go from one side to the other side. I'd probably use a rebound hammer here. Whereas, you know, something like a column or a beam, that's quite easy to get to both sides, so I would tend to consider ultrasonic pulse velocity. In the field, mostly a rebound hammer is used because it has those correlations built into the hammer provided by the manufacturer. Nobody sells an ultrasonic pulse velocity tester that has the calibrations built in. This is an idea that I like a lot, and that's the fusion of data, okay? So you have two different techniques that are giving you two very independent variables about a material, and we cross-correlate those two to get a higher level of correlation. So in this case, there's a method SONREB, which is sonic rebound joined together. So effectively, we cross-correlate rebound numbers and ultrasonic pulse velocities to attain a much, much higher correlation to strength. And this can be used particularly on structures whereby we're unable to confirm strength using destructive testing, because even with a rebound hammer, we would tend to take a couple of cores just to make sure that we were actually estimating it accurately. So this is one of the techniques that would be used where you were unable to take any cores at all. Moving on to concrete thickness. Impact echo is a very interesting technique, okay? So it's related to ultrasonics, but it's much more of a resonance test. And so I've got this slide that describes it, but I want to do it more of a sort of a touchy-feely sort of way. So if I knock on that, on the table there, I can hear the frequency coming off of it. And we know instinctively, by the way that we deal with the world around us, that if that was thicker, that frequency would be lower, and if it was thinner, the frequency would be higher. Okay, so that's effectively what impact echo is. We knock on the concrete and we get our resonant frequency, and then that correlates to the thickness of the concrete, okay? And we do that using some solenoids to impact on the surface. We use a transducer to pick up the resonant frequency, and then we pass it through a fast Fourier transform to estimate what the resonant frequency is. One of the weaknesses of this technique is that as I get closer to the edge, I've got a free edge there, and so the frequency actually starts to change. So the types of applications or the types of concrete elements that I'm able to use this technique on are relatively limited. I effectively need at least twice the width in both directions as I have thickness, because I want to be at least one thickness away from any edge to not get that resonant frequency or a couple of resonant frequencies from having that free edge. Ultrasonic pulse echo is another technique that can be used for the thickness of concrete. And so effectively this is very much more like your traditional ultrasonics, in that we have a transducer, we pass the wave into the material, and we time how long it takes for that pulse to go down, reflect from that density change boundary, the bottom of the concrete, back to our sensor, and then just calculate using the wave speed how thick the material is. This would be something that would ubiquitous to most NDT people. But with concrete, obviously we need to use lower frequency transducers because our material is so heterogeneous. And then also we have the availability of a few things like some what's called a DPC transducer, or a dry point contact transducer, whereby a ceramic tip rubs the surface and creates the wave into the concrete. We can also create all sorts of images from that. This is a C scan that's been taken on a tunnel lining to show you the relative thicknesses. Voids and pore consolidation. So effectively, we don't pour our concrete well, or we drop it from from great height, or we have too much reinforcing, or we don't vibrate it enough, it won't go through the form very well and we end up with holes. So circling back to ultrasonic pulse velocity, we can use this technique for finding voids inside of the concrete. Quite simply, it's going to take longer for the pulse to go around the defect, and so therefore the effective velocity that we get is quite a lot slower. In some cases, we may not even get an arrival at the other side, okay? Circling back again to ultrasonic pulse velocity, because we can create an image using SAFT, which is an imaging process that we can apply to the AE scans. We can create an image and therefore see the actual defect inside of the material. So this was some clay that had been introduced into the aggregates that was obviously weaker than the aggregates, and so they were quite interested in finding that in this paving. And then the impact echo. You know, I've showed you that we would get one frequency if we had a nice solid piece of concrete, but if we have cracking or voids or layering, then what ends up happening is that we get a lot more frequencies, or sometimes it's quite difficult to pick up, you know, any distinct frequencies, in which case we have honeycombing, which is where we have very small distributed voids within the concrete. I've separated cracking from voids and because they're quite different, and there are a lot of reasons why concrete can crack. It's not just about, you know, structural issues, and it's not just about corrosion. It can be to do with how much water was put into the concrete, whether it was dried too much as it was being set. You can see there's a whole bunch of different reasons that we can have cracking in concrete. From a testing point of view, actually the most important thing is the orientation of the crack, whether it's into the surface or whether it's a delamination, okay? And using the ultrasonic pulse velocity technique, there is a methodology that we can measure crack depths for cracks into the surface. And it's just a very simple trigonometry where we place the transducers onto the surface and pass the wave around the crack. We double the distance, and then we can measure how deep the crack is. There are a few issues with this particular technique. It's really the only technique that we have for this application. First, if water gets into the crack, obviously the waves are just going to get straight through. If we have a lot of post-tensioning, the crack will be pulled together quite strongly, and the wave can actually get through. So that's a relatively limited technique, but probably the only one that's available. For delaminations, we can obviously use something like the ultrasonic pulse echo, which I've introduced before. So these are some precast panels with some delaminations inside of them. Okay, so concrete corrosion. Okay, we've gotten to the last application. I know I've flown through quite a few, but I just wanted to show you again that sort of range of different techniques and different applications that we can use for them. So corrosion inside of reinforcing in concrete is effectively a mechanism where we have these different chemical reactions occurring, but if we can stop one of those occurring, or if we can starve the reaction of one of these reagents, the reaction doesn't occur. And so the main thing is that at our anodes, we have the formation of our Fe2O3, which obviously has about 7 times the volume of the steel and creates that tension inside of it. But then we have these cathodes as well. And the main things that are going to create the environment where corrosion will occur will be chlorides, water, oxygen, carbon dioxide, affecting the pH of the concrete. And so we've got this whole mechanism that's occurring inside of the concrete. One of the tests that we can do, whenever people talk to me about corrosion of concrete, of steel inside of concrete, I sort of say, you know, there's a toolbox of techniques that you need to use, because we can't actually see how much steel we have left, how much section loss has occurred. So the first technique that you'll lead them to is resistivity. So, you know, how resistant is the concrete to the movement of anodes and electrons within the concrete? Obviously, if we can prevent that conductivity from occurring, then corrosion isn't going to occur. Resistivity is a method by which we can measure that resistance of the concrete per unit volume, and we can correlate that to how well chloride ions would penetrate through the concrete, but then also we can correlate that to corrosion rates. So it's quite a simple test. We just hold it onto the surface. Stop. I'm obviously going over. Okay, so I'm almost done anyway. So look, resistivity is a really strong technique, although a lot of people don't like to use it because moisture plays a really large part in the reading that you get from it. And so you need to control moisture, and that's through the way that you actually carry out the test on site. Half cell potentials is another technique that's used a lot. Okay, so what we're doing is we connect the reinforcing to a voltmeter and then through to a half cell. And what we do is we place the half cell onto the concrete, and what we're creating is effectively a rudimentary battery, because the steel inside of the concrete is one half cell and then the reference electrode is the other half cell. We then have this potential difference, or this flow of electrons. And so what occurs is that where we have our anodic sites, where we have our corrosive sites, we would tend to have a much more negative potential difference to our reference electrode. And as we pass it over the surface, we tend to grid up the surface, and then we show the contrast of these different potential differences over the surface. People like to use a very simple, a criteria for determining whether they've got corrosion from this half cell potential technique. The issues are quite simple. We're not measuring the potential difference at the bar, we're measuring the potential difference at the surface as a function of the concrete that we're dealing with. And so one of the things that could change this would be purely just how far away we are from the anode, so that the cover thickness. You know, on the same application, we could have quite a different reading, even though it's effectively the same anode that we're looking at. The resistivity of the concrete can also affect this. So if the concrete is very dry on the day that we do the test, then we tend to find that the electrical field is quite small, and so then the readings that we get from the surface are quite low. So there's a lot of different criteria that are used in standards, and this one here is used all over the place. It's a very simple ASTM standard, and that's why people like it, and it just basically says you get this number, you get this occurring. But actually it's a very poor for most applications, apart from where the data that were used to formulate this was taken, which is bridges with de-icing salts in the US, nothing to do with marine environments that we deal with mostly here in Australia. This is my last one. So where I was getting to is that we can actually formulate our own criteria by doing statistical analysis of the data, okay? And so effectively what we do is we have two populations, the anodes and the cathodes, and if we take enough data and we graph this out, we can actually determine what the average of the active areas are and what the average of the passive areas are. And so therefore we can use the data to formulate the criteria that we use to investigate the structure. So thanks so much for listening to that. Hopefully you took something away from it and learned a little bit about the different types of techniques that we use for different applications. Cheers.
Thank you, Ruben. It's a fascinating survey. I didn't realise there's so many things could be thrown at a simple thing like concrete, so it was very informative for me. Any questions from the room?
Just like uni, good stuff.
It sounds like there's a lot of technical things behind some of these.
Yeah, I've brushed over a whole lot of stuff.
You talked about you primarily sort of selling equipment. It sounds like you actually need to provide maybe a bit of support to the use of that equipment as well. How does that sort of work in your business?
Look, we provide training with everything that we sell. So I've gone out and used most of the technology in anger, and so we generally, because we're trying to promote construction NDT, we also want to provide the testing with it. There is no certification for this type of testing, and so it's kind of the Wild West when it comes to actually being able to go out and do it. Anybody could buy a Schmidt hammer and take a test, and nobody's ever going to ask, what was their certification. So just to protect ourselves and make sure that, that the industry continues to grow, we try to throw in some training with that as well.
Yeah, very good.
Yeah,
Okay.
cheers.
Thank you very much. All right.